Okay, and welcome to this video where we look at exponential modelling and growth and decay. Modelling as a concept is fairly common in the A-level course, and you've got to be able to look at everything in context. So, there are two types of exponential equations that you could be asked to look at. The first is where we've got a positive power, which represents an exponential growth, providing a is greater than 1. So this could be used in sort of context dealing with population growth, compound interest, or anything else. If you've got a negative power, that represents exponential decay, and that could be looked at half-life of radioactive substance or car depreciation in terms of value. Okay, right, so most questions in A-level maths deal with things as functions of time. Obviously, if something appreciates in value, means it increases value. Something depreciates, it means it decreases in value. So you've got this example here, which is fairly typical of what you could see. You've got a population of a country in millions, and it can be modelled as such: P equals 14 e to the power of 0.1 t, where t is time in years after 2001. You have to read these sorts of things carefully. So, part A, use the model to estimate the population in 2003. Well, if this model is for time in years after 2001, if that value of t is for time in years after 2001, then for 2003, the value of t will be equal to 2. So the population estimate will be 14e to 0.1 times 2, which is 0.2. So when you type that into a calculator, 14 e to the power of 0.2, you get 17.1 million as an estimate, okay, for the population 2003. Part B, interpret the meaning of the value of 14 in the model. Now this is a very common question, and I always say to my students that the value at the beginning, in the first line which they give you the equation, the first thing I'll say to my students is type in t equals 0. When you type in t equals 0, what do you notice? Well, if you type in t equals 0, you get 14e to the 0, which is 14. So 14 actually represents the population when t equals 0. So in this context, population at 2001. Okay, or in 2001. Part C, show that the derivative of this equation, dp over dt, is equal to kp, where k is a constant. State the value of k. Right. Before we answer, let's just differentiate this first. So, if you remember how to differentiate, okay, now obviously this is not dy dx, but we can use the same principles. Remember the previous video, you look at the power, 0.1t, you treat that as 0.1x, differentiate that in your head, that's 0.1, you bring it down and you multiply by the 14, which will get you 1.4 e to 0.1 t. Okay, now what they want is kp. So we have got 1.4 e to 0.1 t, so we need to replace something here with p. Okay, now this here, if you think about it, this was originally 0.1 times by 14 e to 0.1 t, and hold on, isn't that p? So actually this expression could be rearranged as 0.1p. Okay, so let's just recap. You differentiate this equation, you get 1.4 e to 0.1 t. If I sort of break that down, what I just did there, I'll go 0.1 times 14 e to 0.1 t. This is all p, so it's 0.1 times p, and k is 0.1 then. Okay. Right, D. Interpret your answer for part C in the context of the model. So that basically means, if you look at this carefully, dp over dt equals 0.1 times population. So that basically means the rate of change of population over time is a tenth of the population at that time. Okay, so let's just write that down. The rate of change of population is a tenth of the population at the time. Okay. Part E. Explain why this model might not be appropriate over a long period of time. So, let's think about what happens as t approaches infinity, or we have larger values of t. So let's say we had t equals 1,000. So if I had t equals 1,000, so I have 0.1 times 1,000, I'm going to get a very, very large population. Okay, 3.76 times 10 to the power 44. What happens if I had another 0? Doesn't really work. So the model is not appropriate over a long period of time. Well, if you think about real life factors, will we always have a constantly increasing population? So it's not realistic for a population to constantly keep growing and grow infinitely. Okay, so it's not realistic for a population to constantly grow to an infinite value. Okay, so this model has its limitation. And obviously, if you sort of think about world population today, there is a certain time at which the population of the world will actually level off at a certain value. Okay, so it's not always going to be increasing. And part F, sketch a graph of P against T. So obviously you would need a ruler and pencil for this. This is where my ruler comes in handy. So we've got population against time. Obviously time represents value after 2001. So when t equals 0 is 2001, which obviously had a value of 14 million. Okay, now we know this is a growth graph, so p is 14. And obviously 2 years later, in 2003, it was at 17.1 million. Okay, so we can have our exponential graph like that, okay, or something similar. So obviously that's what we have for the time being. Right, and that's the end of the question. Again, this is a very important topic, modelling with exponential functions. This is a growth question. There are obviously depreciation questions, and you'll see a certain format coming out with all these sort of questions. The more practice you do with the textbook pages, the better it will be for you. That's the end of the video.